All right, today we're going to cover Unit 2, the decibel from hell. That's how a lot of people describe it. It's a strange topic. There's a lot of people who hate describing the decibel because it freaks them out. But basically, I try to explain it in a way that I wish someone had explained to me. And hopefully that makes things clear for all of us. And I hope you've managed to print up your trusty dusty notes for Unit 2. I'll share screen, of course, showing you my notes, as well as the PowerPoint that appears with it. And in this particular 2-week session, this week and next week, Unit 2, we are covering that other dimension of sound, not frequency. Leave that puppy in the rear view mirror. It's gone. Okay, we're talking today sheerly and purely on sound intensity. What was the amplitude of the sound? Frequency, wavelength is one dimension of sound. Amplitude is another dimension of sound. And the unit for frequency was hertz, capital H, small z. Today, the unit for intensity is little d, big B, decibel, dB. We'll always be talking dB, decibel, from hell. So, if I take a look at this thing here, and we talk about the decibel, intensity, decibels, power, and pressure, and now I'm going to go to good old share screen, share my desktop. I'm going to take a peek at these here notes, and let's pull these guys up right here. And you will see what I'm seeing. And I'll tell you what you can ignore and what you should pay attention to on these pages. One thing is, for certain, read Lassen Woodford, okay, your readings on it. And then you can read some kind of intelligentsia kind of talk. In physical, not psychoacoustic terms, intensity is completely independent of frequency. In physics, the acoustics, and not the perception, psychoacoustics, not perception of sound, just the reality, the actual intensity of sound, as would be measured by a scientist. Intensity is completely different from frequency. On a waveform, intensity is represented as the amplitude, the height. The axis, as you know, on a wave is time horizontally. The vertical axis is amplitude. Reading with me, intensity is measured in decibels, little d, big B. First, some terms relating to intensity. Force. Force equals energy. And people measure force in all kinds of different ways. Some people measure it in dynes, D-Y-N-E-S. We will use that. Some people, especially up here in Canada and in various European countries, they measure it in newtons or pascals. Oh well, no big deal. Doesn't matter. Pressure, the next definition. Very important one. So force is energy, and pressure is force over an area. Always, pressure is always something over something, like a fraction. Now, to make this make sense to you, I'm going to stop sharing my screen, and I'm going to look at you all straight in the face, and I want you to kind of do this with me. Press with your hand against the side of your face. And now press really hard, for sort of put a lot of, okay, now stop. Now with the same force, press against your fingertip. Do that now with your fingertip. The same force. Hurts, doesn't it? This doesn't hurt. This does. Pressure is force over an area. Okay? Excuse me. That's why skinny bike tires have more pressure than thicker car tires do. Oh. That's why a knife can cut through bread. I can't use the side of my hand to cut through bread. It's too wide. But a knife, pressure is force over an area. So the blade of a knife is really skinny. So it'll cut right through. Okay, very important. Pressure is force over an area. All right, now I'm going to share screen again, back to our notes. Sound, okay, power. Now we're going to look at power, the third one. And we won't spend a lot of time on power, okay? It's mostly pressure. Power is another way to represent intensity, okay? Power is related to the capacity to do work. What's that? Well, power is a more complicated measurement of intensity. It involves time. How much work was done over time? And you know what a unit is to measure power? It's watts, like your light bulbs. How many watts? Is it a 100-watt light bulb? 40-watt light bulb? How many watts is the bulb? Watts is a measurement of power. Dynes is a measurement of pressure. And if you read the bottom here, right where my arrow is showing you here, intensity of a sound, where I've graded out, intensity of sound can be measured in either pressure or power. We choose pressure. Why? Because it's easier. It's more fun. And also, the ear works like a pressure device because sound hits your eardrum, just like sound from your mouth hits the microphone. Okay? The pressure of sound coming out from your mouth hits the mic. The pressure of sound from outside hits your eardrum. So think of the ear kind of working more as a pressure device. The ear receives sound. The ear doesn't produce sound, it receives it. It works like a pressure device. Before we throw away power, though, we don't want to dump it completely. I want to just emphasize to you how big the range of sound intensity that we can hear. Now check this out, okay? How big is the largest sound we can tolerate before we say ouch, compared to the softest sound it takes to just barely hear? What's the ratio? How much bigger is it? Okay? What's the range of intensity from the softest to the loudest that we can hear? Now this is weird. Check this out. Power looks at what was produced, like in work done, blah, 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 measured in joules, 1 joule, I don't really care, who cares? The usual unit for sound power is watts per centimeter squared. Now the power required for a human to hear a 1,000 hertz tone, not 2, not 500, just 1,000 hertz. Why do we pick 1,000? Just because it's a nice, easy number. It's right in the middle. There's frequencies lower, there's frequencies higher. 1,000 is kind of in the center of the range of hearing that we test hearing. We test hearing from 125 hertz to 8,000 hertz, and we got 7 different octaves: 125, 250, 500, 1,000, 2,000, 4,000, 8,000. Here, how many? There you go, 8. Anyway, 1,000. So we choose 1,000. Flip a coin, yeah, choose 1,000. Okay. How far away from a speaker? 1 yard, about 1 meter. And what listening condition? 2 ears. So you got 3 things here. 1,000 hertz tone at 1 meter distance, here with my finger, at 1 meter distance with 2 ears. What was the softest it took for a normal hearing human to hear that tone? Well, what was the softest power? Check this out. The smallest power required for a normal hearing human to hear a 1,000 hertz tone at 1 meter distance with both ears is 10 to the minus 16 watts per centimeter squared. Now that is going to be a 1 with about 15 zeros in front of it. It's going to be 0.0000000, you know what I mean? Tiny, 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 little idiotic, tiny thing. Compare that to a 100-watt bulb. Okay, we're talking tiny. And then What's the loudest power that we can tolerate? What's the loudest at the 1,000 hertz tone at 1 meter distance with both ears before we say ouch? And the loudest we can tolerate is 10 to the minus 4. So that's going to be like a 1 with 3 zeros in front of it. Okay, it's going to be still small, but still a lot bigger. So how much bigger is 10 to the minus 16 compared to 10 to the minus 4? A trillion. It's a 1 with 12 zeros. Look at it. 10 to the minus 16 is 1. Look at it. You've got 3 zeros is 1,000, 6 zeros is 1,000,000, 9 zeros is 1,000,000,000, 12 zeros is 1,000,000,000,000. Okay, we're talking. So the loudest we can tolerate is 1,000,000,000,000 times more powerful than the softest we can just barely hear. Now, you'll be thinking, well, that's weird. How can you test hearing like that when you've got a range of 1,000,000,000,000? If you got 1,000,000,000,000 different increments. Think of a thermometer with 1,000,000,000,000 different degrees on it. How can you test hearing like that and make sense to somebody? You got your number range is way too big. I like Mozart, but way too many notes. It's too busy. So we go, let's leave power alone. Let's talk about pressure. So I'm going to go to pressure, moving my notes up here. Let's talk pressure. Pressure looks at what's received on a diaphragm, like a mic, or like your eardrum. And that's what it says right here. Okay? The common unit for pressure is dynes per centimeter squared, not watts. Forget watts, dynes. And don't worry about this stuff here. Blah, 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 blah. Okay, that's all just blither blather. Blather, blither, blither, blather. Who cares? Next, this is what you want. Pressure is force over an area. Again, don't worry about newtons. Don't worry about pascals. That's all blah, 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 blah. There's where I underlined. The reference for sound intensity. It's the smallest pressure or the smallest pressure, power I should say, required for a human to just barely hear. Now I'm highlighting this because you know this is going to be on your next quiz, and you know this is going to be on your midterm and on the final, because this is one of the anchors, the cornerstones of the field of acoustics. The reference, the ground, the softest it takes, to the softest pressure or the softest power is that's required for a human to hear a 1,000 hertz tone at 1 meter distance with 2 ears. Those 3 conditions. That the largest sound pressure that one can tolerate. Okay, let's stick to pressure. At 1,000 hertz tone at 1 meter distance with 2 ears in terms of pressure, what's the softest pressure it takes to hear that 1,000 hertz tone at 1 meter distance with both ears? It's 0.0002 dynes per centimeter squared. A 2 with 3 zeros in front of it. Not 4, not 2. It's 0.0002 dynes per centimeter squared. And what's the largest sound pressure? Look at the next line. What's the largest we can possibly tolerate before we say ouch? It's 200 dynes per centimeter squared. So the softest, look at the loudest here, 200, is 1,000,000 times larger than the softest. Do you see that? It's 1,000,000, not 1,000,000,000. But so that's looking better to us. That's way better, because 1,000,000 is a lot less than 1,000,000,000. In fact, 1,000,000,000,000 is 1,000,000 millions. If you go 1,000,000 times 1,000,000, you've got 1,000,000,000,000. Okay, and we've done something here. We've reduced the amount of increments. And now I'm going to show you a picture of what I mean. Look at this picture in your PowerPoint. Do you see that? You'll see a mouse and you'll see 5 elephants. Okay, from and then you'll read here, a dynamic range of 120 dB represents the ratio between the weight of a mouse and that of 5 elephants. Yeah. So the mouse is the softest you can hear, and the 5 elephants is the loudest you can tolerate. Well, we're going to get back to that. Hang on a sec here. What I want to talk about here is I want to show you a picture of 2 thermometers. Here you go. I'm going to blow it up and make it bigger too. Okay? You're looking at 2 thermometers here. One thermometer is the way we tell temperature in Canada. It's called Celsius. And the rest of Europe uses it, Africa, South America, Asia, everyone except England and the United States. You guys tell temperature in Fahrenheit. Okay, nobody else does, but that's what you do. Doesn't matter. Doesn't mean you're not nice people. I'm an American too, so that's just basically the way it is. But look at the thermometers. They're the same height. Okay, and now look at the red. Look at the red where it says comfortable room temperature. You read that? On the right, you guys like temperature around 70, 72. And you say that's comfortable. In Canada, that's about 22 degrees. If a room is 22 degrees, that's comfortable. Now, is it any warmer in my room or colder in my room? The temperature is exactly the same. We just use 2 different thermometers to measure the temperature. Let's look at the bottom here where it says water freezes. Can you see where my cursor is here, where water freezes? In USA, freezing is 32 degrees. Everywhere else, freezing is 0. Get it? Now, if freezing is freezing is freezing. When the ice pond freezes over and there's ice on top of it, that means it's freezing. And it's no more colder anywhere else. The freezing is freezing is freezing. But it's called 32 by you, and it's called 0 by me. Now, if you go way up to the top, look where my cursor is here. Water boils. You see that? And where water boils, you guys call that 212 degrees. We don't. We call it 100. Now, again, look at here's now Celsius. You can think of that. Make this just as an analogy. It's just like a story I'm telling you. Celsius is like pressure. Fahrenheit is like power. Okay? What's the loudest you can tolerate in terms of power? 10 to the minus 4 watts per centimeter squared. What's the softest power you can just barely hear? 10 to the minus 16. Whoops. 10 to the minus 16. In pressure, go to the left. What's the largest pressure you can tolerate? 200 dynes per centimeter squared. What's the softest pressure it takes to just barely hear that 1,000 hertz tone? 0.0002. Now read with me below. 200 dynes per centimeter squared is 10 to the 6, larger than 0.0002. In English, what's 10 to the minus 6? A million. It's 10 to the 6, that's a million. Count the zeros. 10 to the 6. Now go to the right. 10 to the minus 4 watts per centimeter squared is 10 to the 12 times larger than 10 to the minus 16. What's 10 to the 12? Oh, that's a trillion. That's a trillion. Count the zeros. Now, look back to your thermometers. Hey, freezing is freezing is freezing. Boiling is boiling is boiling. Okay? 200 dynes per centimeter squared is the same as 10 to the minus 4. And 2.0002 dynes per centimeter squared is the same as 10 to the 16 watts per centimeter squared. They're just talking different languages. One's talking Polish, the other one's talking German. Okay? It doesn't matter. It's all right. What it means is, in Fahrenheit, look at the degrees. They're tinier. They're stuck together. They're much... Whereas in Celsius, it's more chunk, 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 chunk. They're bigger. The increments are bigger. Not the range. The floor to the ceiling. The floor of just barely audible to the ceiling. is the same. That decibel distance isn't any different. It is the same. It's just that you can talk about that decibel distance in terms of power, or you can talk about it in terms of pressure. And we prefer pressure because from the bottom to the top, there's only 1,000,000 increments. Whereas in power, from the bottom to the top, there's 1,000,000,000,000 increments. Okay? All right. Back to our trusty dusty notes. Good stuff. It's a conceptual thing. Okay? So, hearing science and audiology uses pressure because the ear works as a pressure device, like a microphone. Pressure, force over an area is easier to calculate than power, work done over some unit of time. So now we get to the fun stuff. The range of hearing is huge, as you can see, from the softest to the loudest. That range is so stinking big that we need a number system to handle it. We can't sit there even dealing in 1,000,000. I don't want to say that, excuse me, good grief. I don't want to say that Kelly's hearing is 412,000 and Carly's hearing is 624,000. I mean, and Ted's hearing is 19,000. Who wants to do that? That's still way too many. It's still too many. 1,000,000 is still ridiculous. So we've gone from 1,000,000,000,000 to 1,000,000, but we've got to make it down to numbers that we can handle. And the way we do that is with logarithms. Don't hate me. I'm not a mathematician. I'm not going to foist calculus on you. This is what I want you to understand. We're going to go to the pictures now, and I'll show it to you. It drives me bonkers when people don't explain things, okay? Look at these. This is out of your textbook. Last 10. 10 times 1 is 10. 10 times 10, you've got two tens here. 10 times 10 is 100. What's the logarithm there? 2. 10 times 10 times 10 is 1,000. What's the logarithm there? 3. 10 times 10 times 10 times 10, 10,000. 10 times 10 times 10 times 10, 10, 10, 10, 10, 10. Okay, you keep multiplying. Your numbers go up logarithmically. Okay? And that's what we do with the decibel. Look at this. Here's the picture. This is one of the most important pictures in our talk today. We'll be coming back to this one numerous times. I'll make it bigger so we all look at it. Here's on the bottom, horizontal is dynes per centimeter squared. Right away, you know we're talking pressure. How come? Because the unit isn't watts. It's dynes per centimeter squared. Think of the hand against the face, fingertip against the face. Pressure, okay? This is the pressure unit. Forget power. Screw it. Throw it away. Gone. The softest you can hear, look where I'm circling, 0.0002 dynes per centimeter squared. The softest pressure required for a normal hearing human to hear a 1,000 hertz tone at 1 meter distance met 2 ears, yeah? Okay, so if you multiply that by 10, now you're at 0.002. You got 2 zeros instead of 3. You've gone up 20 decibels. 0.02, you've done 10 times 10 now. You're going more. You've gone up 40 decibels. 0.2, now you're at 60 decibels. 2 point, now you're at 80. 20, now you're at 100. 200, now you're at 120. We've just taken a range of 1,000,000 on the horizontal axis because 200 is 1,000,000 times more than 0.0002. So we've taken a range of 1,000,000 and we've made it manageable into a range of 0 to 120. Dig. Okay, this is what I'm trying to describe to you. The decibel is a unit based on logarithms. So 20 decibels has 10 times as much pressure as 0 decibels. 40 decibels has 100 times as much pressure as 0. Okay, 60 decibels has 1,000 times as much pressure as 0, and so on. 200 dynes per centimeter squared has 10 times 10, 6 times. 10 times 10 times 10 times 10 times 10 times 10. Okay, so this is showing you the pressure on the horizontal, and this is showing you the unit of the decibel. And the SPL means sound pressure level. Decibels, sound pressure level. Okay? So when you're talking 60 decibels sound pressure level, which, by the way, that's about the loudness of typical speech. Average speech. My father can beat your father at checkers. Yakety, 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 yak. That's about 65 dB SPL. Okay? And if I'm whispering really soft, that's about 40 decibels SPL. And if I'm yelling at somebody, that's going to be about 80, 85. Okay? And a screaming jet engine is going to be about 120. And then your ears begin to hurt. So the decibel range of our hearing is about 0 decibels SPL to about 120 decibels SPL. But you and I now know we have a little secret, don't we? That floor, that 0 to that ceiling of 120, that 120 is 1,000,000 times the pressure of 0. But shh, don't tell anyone that. Let's just talk about 0 to 120. Because we used logarithms. And that way, we've gone from 1,000,000 increments from the floor to the ceiling, and now we're down to 120. But please don't think the floor changed or the ceiling didn't. The ceiling changed because they didn't move. Just the units that we use to describe the distance changed. Okay? We found a way to make it work so we can manage it with numbers from 0 to 120. Oh, well, isn't that special? Isn't that just special? Okay, here we go. So I'll just read with you guys from the bottom of the page here. I'll share my screen again. All right, this is anyway, there we go. And I'm going to show you, forget that one. Okay, I'll pull out of that. Gosh darn, Ted. Boy, my screen doesn't want to share. Let's see if I can stop sharing here and go back to share. This is weird. I can't get rid of my PowerPoint. It won't let me. See if I can hit. Yeah, it won't let me. I'm just going to read here. I'll just go back to talking to you. The decibel is a unit on the bottom of your page based on logarithms used to define ratios between powers, pressures, or anything. The dB is 1/10 of a bell. It's named after Alexander Graham Bell. Alexander Graham Bell had hearing loss in his family. Did you know that? He was trying to discover a hearing aid. His in-laws had hearing loss. I believe his wife had hearing loss. He was a Scotsman. He invented the telephone. The Americans say he invented it in Boston. Canadians say he invented it in Brantford, Ontario. The truth of the matter is he was a dual citizen of Canada and USA, much like me. Only he came from Scotland. Ach, laddie, you spoke a wee bit of Scotch now, and he ate the haggis. All right now. So he was trying to invent a hearing aid, and he stumbled on the decibel. And what he and he invented actually is he stumbled on the invention of the telephone, but he came up with this thing called the decibel. And he's the one that invented it. Hey, there's someone's pooch in the background. Gotta like that. Hey, take a break. Good stuff. All right. Anyway, so that he came up with the range of the decibel. And a deci is a tenth. So it's a tenth of a bell. He used 12 numbers. He just used 12 to talk about the range. In other words, he did this. He was crazy. He went, boy, something strange happening to my PowerPoint. I'll tell you, I can't advance. I can't go back. There's nothing I can do. Oh gosh, hang on a second here. Oh, there we go. Good. It unstuck. Good. Okay. See this here? He didn't call that one 20. He called it 12. He called this 0. 20 was 2. 40 was 4. 60 was 6. You know what I'm saying? 6 bells, 8 bells, 10 bells, 12 bells. But that's too coarse. That's like combing your hair with a comb that's only got 12 teeth. I mean, it's not enough teeth. So 12 was too few. So they broke it up and made it decibels. So now it's 120. Instead of 0 to 12, it's 0 to 120. That's the only difference. Okay? All right, I got it back again. Somehow things had froze up. I got it back. Yes, healed. All right, so now we are at the bottom here. The decibel is a unit based on logarithms, and it's used to define ratios. And we use it to define ratios between pressures. The dB, it says here, is a tenth of a bell, named after Alexander Graham Bell. It's based on logarithms because it compresses a huge linear range of numbers into a smaller one. And the ratios always compare some sound intensity to the ground. Now, this is what I want to make sure we understand. The ground is holy. You are standing on the ground, okay? It is the softest it takes for a normal hearing human to hear a 1,000 hertz tone at 1 meter distance with 2 ears. And what pressure was that? 0.0002. And what do we call that? 0 decibels SPL. So this ground, right where I'm showing you here, that corner, that's the ground. That's the reference. And I'll bring it down home so it makes more sense. If you want to talk about the height of an apartment building compared to the height of a house, you've got to know where the ground is, right? You can't talk about the height of the house compared to the height of the apartment building unless you know where the ground is. The ground defines the bottom. And now you can talk about how tall the house is and how tall the apartment building is. It's the same thing with sound. Everything is anchored around that 0. That's what we call 0. But please don't think 0 means no sound. It doesn't. What did we say 0 was? The softest it took for a normal hearing human to hear a 1,000 hertz tone at 1 meter distance with 2 ears. For a cat, it might be different. Okay, for a dog, it might be different. We have to call 0 something, so we arbitrarily, deliberately chose to define it as the softest pressure required for a normal hearing human to hear the 1,000 hertz tone at 1 meter distance with 2 ears. Somebody decided in his infinite holy wisdom, just said, what the heck, that's what we're going to do. So that's what we did. That's what 0 is. And everything is compared to that anchor. Okay? It's a very important concept. I want to make sure we have it down. Okay. Excuse me. Measurements also. Measurements in logarithms correlates well with psychoacoustic perception. 60 dB sounds about twice as loud as 30. Well, yeah, big deal. The bottom of the page. Power equals pressure squared. Put a circle around that puppy too. Power equals pressure squared. That makes sense because 1,000,000 times 1,000,000 is 1,000,000,000. Huh? Okay. The softest power, 10 to the minus 4. Greatest power, 10 to the minus 6. What's the difference? 1,000,000,000. Go to pressure. Softest pressure, 0.0002. Biggest pressure, 200. What's the difference? 1,000,000. Okay, freezing is freezing is freezing, boiling is boiling is boiling. The range didn't change, just the number of increments, the number of fingers. Okay, power equals pressure squared. Doesn't matter, the range is still the range. Okay. Top of page 2. Top of page 2. All righty. Move our way down, and we'll talk about a guy who lived in a van down by the river, and his name was S.S. Stevens. He is someone who said, you know why the decibel, let's talk about the decibel being based on ratios and logarithms here. There are 4 ways to assign numbers to things. Now I'm going to show my face here again. I'm just kind of, sorry, you got to look at my ugly mug here. Okay, so there's 4 different ways to assign numbers to things. One way to assign numbers is to name them, like football jerseys or basketball things. You're number 9, you're number 22, you're number 12, that's your number. It's just naming. I'm just naming you with a number. The second way involves not only naming, but now you are ranking. I'm going to put you all in a line from tallest to shortest. Okay, the tallest is number, or the shortest is number 1, the tallest is number 12, or what have you. Now I'm ranking. I'm not only naming with the numbers, but I'm ranking in terms of height or intelligence or how fat you are or whatever, you know, just picking something to rank you on. And that's called ordinal. So when you read on the top of page 2, that's the second heading, ordinal. Now, ordinal is often used in statistics. Oh, we're the 3rd largest hearing aid company in the world. Yeah, right. The first hearing aid company is up here. The second hearing aid company is right here. And the third hearing aid company is way down here. Okay, what was the horse that came in third? The first 2 horses may have come in neck and neck, and the third horse was an entire lap behind. Well, it doesn't matter, he came in third. Well, you ranked him. Okay, so ranking is okay, but it's not very picky because it doesn't say that there's equal intervals between each item, like inches on a ruler, or like temperature in degrees. For that, you need the interval scale. That's the third way. You've got a nominal is naming, ordinal is naming, and now you're ranking. Interval is you're naming, you're ranking, but you are also saying you've got equal intervals between each item being ranked. It's not like, I don't know, okay, this one here, 1, 2, or 3. The intervals aren't equal, okay? Think of 10 horses in a race. You've got the first 2 horses are right neck and neck, and the third horse is a whole lap behind, and the fourth horse is right behind that third horse. That's ranking. Ordinal says, or I should say interval says you've got equal intervals between each item being ranked. Now, this is important for our field because this is how people talk about satisfaction with your hearing aids. I'm going to just digress here. You know what you're going to study next year when you're in year 2? You're going to be studying satisfaction questionnaires. How happy are you with your hearing devices that you've been sold? Okay. Do you like them? Number 1. Are you, so-so? 3. Do you hate them? 5. Guess what they're doing there? They're trying to map your emotions, your feelings, onto an interval numerical scale. Because the distance between 1 and 2 is the same as the distance between 2 and 3, which is the same as the distance between 3 and 4, which is the same as the distance between 4 and 5. So you've got 5 little fingers, and you love the hearing aids. I like them. You're so-so. Yeah, I don't really like them. Hate them. Okay, you got 5 different numbers now. So what you've done is you've been able to map someone's heart. Valentine's Day. You've been able to map someone's feelings onto an interval numerical scale. And you know why that's so important? Because now you can do statistics. That's exactly what government agencies do all the time. How happy were you with your service at the bank? Fill out this survey. Answer the questionnaire. They take all those questionnaires and guess what? They've got everyone's feelings on an interval numerical scale. They can shove it into a computer and do da-dum, da-dum, da-dum. Well, the mean average feeling about this was number 3.5. And that's what they publish in the ads. It's not bad. It's just, this is just how this kind of stuff relates to our field, aside from the decibel. Anyway, the fourth way of assigning numbers to objects is called the ratio scale. And the ratio scale says, excuse me, not only are you naming, not only are you ranking, not only do you have the same increments between each item being ranked, but now you've also defined the ground, just like we said with the decibel. So you've got ordinal, yep, you're naming, I should say, nominal, ordinal, you're ranking, interval, you got equal distances between each item being ranked, and lastly, you've defined what 0 is. Now think with me here. That's what you're doing with the decibel. The decibel is based on the most complex way of assigning numbers to objects. That's why we're talking for at least an hour on this today, to try and highlight what logarithms and ratios do. And now pull this back to temperature. If it's 60 degrees outside, I'll talk Fahrenheit language. Okay, if it's 60 degrees, is 60 degrees twice as warm as 30? Not really. It's 30 degrees warmer than 30, but is it twice as warm as? If it's 40 degrees outside, is that twice as warm as 20 degrees? Not really. It's 20 degrees warmer than 20, but it's not 2 times. If you want to say twice as much as, you have to define a ground. See, if an apartment building is 2 times taller than the house, you have to define the ground. And that's what you're doing with the decibel from hell. Okay, so we've covered lots of weird material. We'll look at page 2 and I'll tell you what you need to ignore on page 2 and what we should focus on in page 2. And then we'll be reaching just about the close of what we're doing today. Time flies when you're having fun, okay? Or as they'd say in Latin, tempus fugit, time flies. Okay, so here we go. You're looking at your notes, page 2, and your 4 ways to assign numbers to things, and we covered it. Done. Then you look at the second heading.
Our number system is based on logarithms of base 10.
Well, again, don't freak. It just 10 to the 1 is 10. That means 10 by itself is 10. 10 to the 2 means 10 times 2. That's all. That's all that this little area right here is talking about, the same thing as this area right here. Okay? Good. Same crap. Okay, back over here. Audiologists and HISs measure sound intensity in terms of sound pressure. We don't use power, we use pressure. And to do this, we use this little formula, and I'm never going to ask you to sit there calculating all this stuff, but you need to know what it is. The formula N just means whatever, X. It just means of some decibels, SPL, is equal to, so just you could put 60 in there, you could put 40 in there, you could put 20 in there, doesn't matter. Of some dB SPL is equal to 20 times the logarithm of some pressure over the reference, and the reference is the ground. That right here, what I've grayed out, that's the ground. That's the holy ground. That's the softest it takes for a normal hearing human to hear the 1,000 hertz tone with 2 ears. That's what we call 0. So that bottom denominator, that bottom number of the fraction is always the same. It's always going to be 0.0002. Why? Because that's 0 dB SPL. And if you're wanting to find out what some pressure is, and you're wanting to find out what is, so let's do an example. Here, first you do the ratio. First you do this, what I'm circling right here. Then you find what's the logarithm of that ratio. Then you multiply it by 20. There's 3 steps. First you calculate the ratio. Then you find the logarithm of that ratio, and you multiply it by 20, and that gives you your decibels SPL. Let's do an example. For example, 0.002. What if you had a pressure of 0.002? How many decibels is that? Well, so this is what you're trying to find out. You're trying to find out by this whole formula, what you're doing is you've got some pressure in dynes per centimeter squared, and you want to find out what decibels it is. Okay? That's what you're doing. You're always going, you're looking at this guy here. Whoops, not that one. You're looking at one of these numbers here, and you're saying, what decibel is that? Okay, so that's what we're doing. You're seeing some pressure along the horizontal, and you're saying, what decibel is it? So you can always look at the graph and tell me what that is, but we want to be able to figure it out this way. So that's all we're doing. So let's say you had some pressure of 0.002. That was your pressure. You're going to put that over top of 0.0002. And 0.002 divided by 0.0002 equals 10. Okay? Just get your calculator and do it with me. You know that. Okay. What's the logarithm of 10? Well, how many times does 10 have to be multiplied by itself to equal 10? 1. So what's 20 times 1? 20. So let's do it on, let's take this picture here. 0.002. You compared that pressure to this pressure. So you put 0.002 over top of 0.0002, and you said that equals 10. So what's the logarithm of 10? How many times does 10 have to be multiplied by itself to equal 10? 1. What's 20 times 1? 20. There you go. Boom. So instead of looking at the graph, you figured it out by using the formula. Let's go here. Do another example. 0.02. If you had that pressure and you were asked, what decibel is that? If you had a pressure of 0.02 dynes per centimeter squared, what decibels SPL is that? Well, you'd do 0.02 over 0.0002, and you'd divide that and you'd get 100. Because 0.02 is 100 times bigger than 0.002. It's got 2 less zeros. What's the logarithm of 100? Well, how many times does 10 have to be multiplied by itself, 10, to equal 100? 10 times 10 is 100. So the logarithm is 2. Logarithm of 100 is 2, because 10 has to be multiplied by itself twice. Okay, what's 20 times 2? 40. So now you look at your graph and you'll see the same thing. 0.02 is 40 decibel sound pressure level. So that's all we did. Here it's visual. The other way was numerical. And if I ever ask you on a quiz or a test, I'm just going to pick one of these numbers here, and I'm going to just say, put it over the top and tell me what it is. Show me what you did. Show me your work. If I asked you what 2.0 decibels is, or what is the dyne, if the pressure is 2.0 dynes per centimeter squared, what dB is it? I'm going to expect that you'll go, oh, you'll do 2.0 over 0.0002, and you'll divide it on your calculator, and you'll get some number. And then you'll do, what's the logarithm of that number? Well, how many times did 10 have to be multiplied by itself to equal that number? So if your picture, if it said 2 point, okay, that's going to be, how does 2 divided by 0.0002 is going to be 10,000. How many times did 10 have to be multiplied by 10 to equal 10,000? 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. Huh, the logarithm must be 4. What's 20 times 4? 80. Okay, Slane and Pimple, good stuff, good. The rest of the page is for nerds. Don't worry or freak about this stuff. You're looking at it, freakest thou not, yea, e'en so verily, I say unto you. Don't worry. This is for the nerds in the class that want to know why it's 20 all the time. What are we doing with this 20? How come it isn't 10? Okay, if it was power, you'd be talking 10. This is just breaks it all down from bells to decibels, power, pressure. You can play with it if you want. I would have to personally be looking at the page to remember it. And if I'm teaching the course and I'd have to look at the page to remember it, why in the Sam Hill would I ask you to be knowing it any better than I do? So don't worry. But I put it in there in case anybody really wants to figure it out. Okay, next, move down the page. Summary description of the decibel table. Now, this is a picture you may see in your readings. Let me ask you if you've got this picture. I'm not sure if you guys have this one or not. Look at this one here. This is just gross. This one here, when I look at this picture, my eyes get tired. I mean, I just look at this and go, do you guys have, let me ask you, are you using the textbook called Martin, Introduction to Audiology? Is that one of your textbooks? I believe this picture is out of that textbook. And there's nothing wrong with Martin. He's a well-known, respected audiologist. He's still with us. He's an elderly gentleman by now, but smart as a whip. But if you just want, if you look at this table, it's just like, oh God. But it's got all these ratios in it, and the logarithms, and watts per centimeter squared, and the watts per meter squared, and decibels intensity level. Ooh. And then you've got equal amplitudes, and then you've got pressure. All along the side is pressure, 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 pressure. dBSPL. What's the dynes per centimeter squared? And you're looking at the logarithms here. Da, da, dee, dee, da. But again, what you're going to see is this relationship here, where I'm circling. This relationship here is the very same thing as this relationship here. Okay? I just like to break it down into a more visual way. Martin is a little bit more intellectual in his way of describing pressure on the right versus power on the left. But at any rate, it doesn't matter. Different strokes for different folks.
That's number 6 on the handout, the number 6 slide on our handout.
I believe it is. Yeah, I think you're right. Yeah, it's number 6. Okay? And the handouts you have are the same PowerPoint I'm showing you here. Exactly. And on my screen here, it says 6. If I go on the left here, you'll see 6. So, yeah. All right. Summary description then. Basically, if I read it to you, and we'll just read this very bottom of the page here where I'm circling right here. 120 dB sound pressure level is the same amount of intensity as 120 dB intensity level. Intensity level is power, okay? Pressure is pressure. So the boiling is boiling is boiling. You see that? Whether you measure it in pressure here or whether you chose to measure it in power. Boiling is boiling is boiling. Here, Freezing in terms of pressure is the same degrees as freezing in terms of power. Okay, these are just two different ways. I'm just summarizing. That's all we're doing is summarizing what we talked about today. Power has 1 trillion increments between 0 and 120. Pressure has 1 million increments between 0 and 120. Power equals pressure squared. Think of it by analogy. Power is a finer toothed comb than pressure. It just has more teeth in it, but the width of the comb is the same. That didn't change. Okay? All right. BC ferries, no reply. Yeah, I live on an island, so I keep getting emails about the ferry system here. It's about a 30-mile trip across the water over to the mainland. We live on the island. It's kind of weird. Anyway, big island too. It's about 300 miles long. It's a huge, long, skinny island. Google up Vancouver Island just for something fun to do. And you'll look at a totally different area, neck of the woods from Missouri or, well, Idaho, you're getting closer. Anyway, power uses 10 times the logarithm power ratios, while pressure uses 20 times the logarithm of pressure ratios. Don't freak. Just leave it. Stick to what we talked about. Okay. And this is just getting out of power and staying with dB sound pressure. The formula for dB sound pressure, dBSPL, is 20 times the logarithm of some pressure ratio. Note the 3 parts, 20, logarithm, ratio. First you calculate the ratio, then you find out the logarithm of the ratio, then you multiply by 20, and that gets you from dynes to decibels, SPL. Okay? Again, to calculate any ratio, you got to know what the bottom is. You have to know where the ground is. To tell if a high-rise apartment is 10 times higher than a house, you've got to know where the ground is. The reference or ground for pressure, what we use, is 0 dBSPL. And what is that in terms of pressure units? Dynes per centimeter squared, 0.0002. Every time you increase the sound pressure level by a factor of 10, you go up by 20 dB. And again, every time you increase the pressure by a factor of 10, look with me carefully. Every time you increase this by 10, you go up 20 dB. That's what this is telling you. Okay? So for example, what's the dBSPL for 20? Let's just do our last example and get out of here. Okay? Good. dBSPL is 20 times the logarithm. So we're trying to figure out, our example is 20. If I gave you a pressure of 20, what decibels SPL is it? On the graph here, you can see it's 100. But let's find out how you got there. First, you do the ratio. 20 divided by 0.0002 is 100,000. How many times does 10 have to be multiplied by 10 to equal 100,000? 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000, times 10 is 100,000. The logarithm of 100,000 is 5. 20 times 5 is 100. Your answer is 100 dB SPL. Told ya. Okay. Next week, we're going to look at more, what is the intensity of various things? What is the intensity of a lot of stuff? And I'm going to, just to give you a preview, I'll just show you what slides here are bogus and what slides are good. Okay, let's look at slide 3 in your thing. Look at this one. Hearing threshold, 0 dB. Breathing, 10 dB. Whispering in the air. Well, you know, this is a bit bogus. It's not really, I find this not really too accurate. It's sort of there, but it's a little bit off. I'm going to just, here's another one here. Well, that's talking hearing loss. Here, look at this one. Faintest sound heard by a human ear. Yeah, that's right. A whisper in library, that's more than 30. Write this down so you memorize it. Ambient room noise. When you're just sitting there like this, ambient room noise is about 35 to 40 dB/SPL. A whisper, about 50 decibels SPL. Average conversational speech, about 65 dB/SPL. Yelling, 80 to 85 dB/SPL. A screaming jet engine, about 120 to 140. Okay? What's the decibel level that starts to cause hearing loss? 85. If you are exposed to 85 decibels for 8 hours a day, you stand in danger of permanent noise-induced hearing loss. Noise pollution is awful in our society. Elderly people in Africa have better hearing than elderly people in North America, and it's because Africa has less industrial noise pollution. Noise is a pollution, and it kills off your hearing. It kills the hair cells in your inner ear. It's like staring at the sun burns out your eyes. It's the same thing. If you can hear someone's headphones and you're not even listening to the headphones, imagine the decibel level smashing into that person's eardrums. Noise after aging, noise is the second most common cause of hearing loss in the world. The sad thing about it is that it's preventable. Can't do much about aging. Aging means you're getting better. Yes. Yeah, let me stop sharing so I can see you. Yeah. Here we go.
What about somebody who plays an instrument in a band?
Yeah, that can do it. It can. There's many musicians who've had hearing loss due to noise. But the good thing, Nisha, is that there's musicians' earplugs. And musicians' earplugs are a special kind of earplug that makes you still able to hear all the harmonics of the music beautifully, but it prevents against noise-induced hearing loss. Google up.
Gotta get some.
Oh, what do you play, Nisha?
So my daughter, she plays the electric bass, and my son plays drums.
Okay.
And they're young. My daughter's 11, my son is 7, but I'm always worried. And then they don't want to put on the clunky ear protection.
Musicians' earplugs. Google them up. They will be custom made for your children. They'll take an ear mold impression and they'll build them to fit their ears, and they're fantastic. Okay, great question.
Yeah.
We're going to be covering more of this, of course, next week. Okay. Anybody else have any question? Carly, you're going to call me tomorrow, right?
Yes.
Okay, cool. All right. Adios, amigos. It's been a slice.
Bye.
You bet. Glad everybody showed. Hello to your mother again, Nisha. Okay. All right. Bye-bye.
Oh, happy Valentine's Day.
Yeah, thank you. Same to you and yours.
Okay, bye-bye.
You bet. Bye-bye.